All right, I think we've got a couple of new things for today. We're going to look at mainly joining pieces together. We'll look at our little guy that we made last time. I painted him up just to see what he would look like. He did work out, except our support material is a little bit too close. Remember, he had to be supported, like his arms needed to be supported. Whoops, he's off the screen. There he is. His arms had to be supported so that they wouldn't just print in midair. Removing that support material was a little bit tough, so we are going to need to make some adjustments to where the distance between like the tip of his fingers here and the support material, how close that is, because right now it's printing just a little too close, and it caused him to break. I did glue him back together, which actually fits in with what we're doing today, because we're talking about different ways you can join your prints. Not all of them are gluing, but this guy obviously not much you can do, because where he broke, you can't really tell too much, but he broke right down there in his leg area, down in there. You can kind of see, I guess, maybe, oh, you can probably see the one on his back foot back there, a little seam, but he's a mummy, so it doesn't really, that's a good thing about printing mummies, is they don't really get too bad when they're all torn up. It did work though. We just need to adjust our support settings so that they're a little bit easier to remove, because these were a little bit too tough, a little too dense. But you know, this is something kind of thing there where we didn't paint the bottom, that you can do pretty easily. It wasn't, you know, that was in our mesh mixing exercise where we just took some models we found off of Thingiverse, mixed them together, chopped them up a little bit, and now we have a new piece that we didn't have before. So those are the kind of things you can do with mesh mixing. You don't have to be able to create geometry from scratch, go into SolidWorks and create things, or go into Tinkercad and create things. We'll talk a little bit about Tinkercad in particular. SolidWorks is probably a little too daunting to try and explain in a single short video, but I think we can explain a little bit of Tinkercad later on, if that's something that you're interested in. I also got another box. It's pretty beat up, but I got another box of sample filament, so I thought we'd open that and see what's inside it. So let's see, where's even the front of this thing? It's kind of hard to tell now. I think this was supposed to be the front. There we go. All right. All right, so this is how they normally, let's see if we can get it in there, how they normally show up. There's usually some announcement about, oh, this is the program where if you refer 3 people, you get a free box. So this time we have ABS low odor. I've never printed ABS low odor, so I don't know exactly what that is. The temperatures are a little bit cooler than what you would normally find with normal ABS. Normal ABS, you usually have to print a little bit hotter, or at least at the upper end of this. It doesn't list a bed temperature. That's interesting. Normally with ABS, you have to have a heated bed for sure, and heated chamber even. It says it's easy to print. Works great on most open source printers. I don't know. Maybe we'll try that later on and see. I don't. The ABS stuff is generally kind of tough. Let's see if we can get that to focus a little better. To print in a chamber that's not enclosed, which our Ender 3 is. Oh, here's some PET material. This one's printing pretty hot, 230 to 250. So the 230, remember we didn't do a PETG temperature tower. Bed temperature is pretty high too. So this one, to print this, according to their numbers here, it's going to be at the upper limit of what your Ender 3 can do, at stock anyway. Odorless composition, low warping. They misspelled strength. A shiny finish, which is kind of typical of PETG, or in this case it's GPET. Translucent look with a natural color. Well, interesting. We got a sticker. Oh, here's a clearish one. I've not heard of this one, Alloy 910. This one's printing pretty hot. Now this one says 45C with PVA. What that's talking about is it might need a support material or I guess they're saying, this is interesting. It says PVA glue stick will work. Okay, I read that as will not work. All right, so PVA is just meaning that PVA is basically Elmer's white glue type stuff, and the glue stick will work. Just most glue sticks are also PVA. So it's saying that you need that as a release agent or an adhesive. I don't know which one. Probably a release agent between the print and the bed. Let's see. The goal was to provide super material with very high tensile yet sufficient elongation. So basically, it's pretty tough material. It says it has 8100 psi tensile. I assume that means tensile strength. That's, you know, decent for a printed part. Actually, that's really good for a printed part. Now, this does not necessarily mean that the layers adhere that well. This one I'd have to send to another printer though. This one starting at 250, I don't think that'd be a good idea to try to print. I actually don't even know if the firmware would let us print 250 on our Ender 3 without overriding some settings. That is, remember, in the hot end of our Ender 3, if you don't change it, there's a plastic Teflon tube inside the hot end or inside near the actual nozzle that probably, if we're trying to heat the nozzle to 250, that area might get hot enough to start to degrade the tubing inside there. So that would be tough to print on Ender 3, I'm afraid. Ooh, this one is got, I don't know if you can, yeah, you can see that. It's got like glitter in it or something. And it's called E-Twinkling PLA. This one prints at regular PLA settings, it looks like. Let's see if it says anything in particular. It's biodegradable, but that's PLA in general. Well, their descriptions are interesting here. It says the appearance of twinkling like feels makes it very popular as soon as it was to the market. Not really sure what they're trying to get in there. I think they're saying that hey, it's kind of neat that it's sparkly. And then down in here, oh, got Starburst. Let's see, eSun sticker, and we can the same kind of box type thing, but for dice. Every month you get a different set of dice, I think. So this one's got some interesting ones. One that we probably can't print, or I'm not going to try to print on the Ender 3 just because of the temperatures. But the others look like things that we can at least try out and print. You get, let me show you. I don't know if it normally says on here. You get 50 grams, 16 meters. So depending on what slicer you're using, you can kind of estimate if you have enough. This is usually enough filament to do several models. Like this little guy hardly took any amount of filament. So you can usually print a decent amount. I don't know if you'd want to print like a temperature tower just to figure out the correct setting. But you usually get enough to print a few things. All right. Let's get into how we might bond some stuff together. And there's different ways. There's mechanical. You can use mechanical fasteners. You can actually build hinges into your print. Obviously, you can glue things. You can use a variety. Let me show you a couple. I talked about this one last time. This PLA Gloop. Now, this is one of the original batches, so it may not even be good anymore. I haven't used it very much. I did open it. Well, I did open the bag and see that it hasn't all disappeared. There's still stuff in there. This material at the back is kind of an absorbent material that, in case it leaks, it will go into that material versus wherever it goes. It melts, or it doesn't melt like with temperature, but it melts most plastics, including PLA. It's kind of rough stuff. It has several warnings on it. Vapor is potentially harmful, so you want to use outdoors or in a well-ventilated area. Now they do have some new versions of this. Let's look at their website to see what they've got going on now. There they are. So they have a PLA, they have a ABS, a smaller ABS, another PLA. Looks like they mainly have PLA and ABS, which are the two primary materials you're going to print in. They also, well, not only are they talking about how strong the bond is, because it basically melts the two halves together and they reform as one solid piece. They also use them as an adhesive on your bed. If you have a material that is difficult to stick down, you can basically paint this material on the bed and print on top of it, and it will adhere most material pretty well. I normally don't have too much peeling problems, but if you're trying to print something that's going to cover your entire bed, then there's a good chance that it's going to warp at the corners no matter what you do. And so this will kind of help hold those corners down. Another thing that I do for if I do have a print that I'm pretty sure is going to warp, in Cura, in fact, let's go ahead and open Cura. Go ahead and start it opening anyway. In Cura or any other slicer, whichever one you're using, you can add a brim to the part, and what that does is, you know how we did the skirt on ours and it prints kind of a couple of traces around it before it actually prints the part itself. It's purging the nozzle and, you know, giving you time to get everything set up. A brim will actually do the similar thing, but it'll be many more, and it will actually connect to the part. So it's kind of like a little flat area that is connected to the part itself. Well, that alone will help hold down the corners, but what I use it for is if I see one to start peeling, that corner peeling up, that brim will also peel up, and I'll just tape the brim back down to the bed. Literally get some blue painter's tape or whatever tape I have and tape it back down as it's printing. Here, let's look in Cura and show one of those. We're kind of getting off. This is sort of related to joining. If you have square parts, they're easier to join. But I guess we are getting a little bit off track of what we're talking about. But I just want to show you this setting. Let's find a part. Where did I put one? I think there's some in here, in these truss pieces. There, yeah, that'll work. All right, so here's a little part. Now it's turned the wrong way right now, so we need to rotate it flat. Wow, I'm having trouble moving. All right, there we go. Now in our slicer settings, there are build plate adhesion settings, and we just have it defaulting to skirt. That's the one. Well, I'm going to show you what it is. It won't take long to slice. All right, so if we look in preview, the skirt is this outer little circle, this couple of laps that it makes around the part. That one you can use. It doesn't help at adhesion at all, but it helps you purge the nozzle and get your bed fine-tuned. Maybe you're adjusting the bed level knobs or baby stepping or whatever. That's what skirt does. Let's go back and change it to brim. And there's raft. We'll talk about that in a second too. Raft can also help with adhesion. So here's brim, and see how it's now there's all this area connected to the part. That can help with the adhesion also, just having all this other material to contact the bed. But also, if you see this thing start to peel up, then you can literally tape across it as it's printing and hold it back down. Since we're here, let's look at the raft also. If you're having trouble getting your bed flat, what this does is, this one looks a lot like the brim except wider, but there's actually several layers to it. You can kind of see here I've got 3 layers, or actually 4 layers. These 4 layers, and I assume there's an option in here if we turned it on to tell how many layers. But what they're doing is they're kind of building an entire surface to print your part on. So what this will do is it gives you a long time to get your bed printing, your extrusion rates right and everything. But it also kind of levels this section of the bed by printing directly on it, and all the unevenness happens in the raft that you're going to throw away later. So your print will happen on top of the raft. So it does add a good amount. Look, we're at 53 minutes with the raft. Without the raft, with the brim, we're at, let's see, 33 minutes. So it added 20 minutes plus a good amount of material. Let's see, we're at 4 grams with the brim. See how many grams of material we're at with the raft. 8 grams, so we doubled the amount of material we're using. And this one's a pretty thin little part, but so it does add a decent amount of material and time. But if you're having trouble, then it is certainly a way to basically level out your bed by printing on top of it, knowing you're going to throw away this piece that might be all sorts of unlevel and have ugly finishes on it or whatever, but you don't care because you're going to throw it away. You're just going to print on top of it and then throw it away. All right, we were saying all of that because in here they were showing that they were using this PLA Goop or ABS Goop, whichever. Probably wouldn't need the PLA Goop, but the ABS is particularly bad about warping. They were painting it directly on the bed. I don't know if they have another. Yeah, they do show it here. So you can actually use this since it does melt the plastic itself. It will also work to smooth out the surface if you wanted to. I don't know how much this cost anymore. Let's see how much it is. Oh, well, maybe we can't find out. I don't know. It was, more expensive than just glue. Here they are. PLA Gloop. This looks like the size that I have over here. Hey, they have a PET now. Now here's a little sample. I actually have one of these samples somewhere. $17, but unless you're using it to do more than just bond pieces together, then that's reasonable for one of your higher end glues. There's just bigger volumes of it. And this, I guess, assume is more of a gel. I haven't used this glue goop. I assume it's more of a gel. All right, so let's see. I don't really have a lot of protective gear on, but I'm in a pretty well ventilated area, so let's just see if I can find some stuff that we might if I can get all the screens to go away. Let's see which other one is in the way. Oops, not that one. There. All right, we got them all. We need something to attempt to glue together. I've got some pieces here that I have used in another class for trusses. Oh, you know what? We've got these little cubes that we printed early on, the calibration cubes. These guys. So let's see how this looks. I'm going to kind of do this on this mat in case we spill some, and we'll just try to do something like that. All right, it comes with a bent up but there little deal, and it is very gloopy for sure. We just put a little. It doesn't give you any actual how to apply it in here. Now maybe on the website they do. Nothing in particular. Basically, oh, I was supposed to shake it. There's not much shaking happening there. All right. So it's tacky enough that it holds itself in place, and it felt like it was, one of those type of glues that actually goes in and does melt the material. It doesn't tell me over here how long really for it to set up, but we'll come back to it in a second and see what it's like. Now again, this is an older, I don't even know if it has a date on it. No, it does not that I see. But this is one of the original, I can't remember if they did a Kickstarter or what, but it is one of the original bottles of it, so it could be that it's gonna need a little more time than what they currently offer. It didn't smell though. I didn't I didn't smell it directly, but it didn't have enough vapor that it was bothering me from here. It's pretty solid. I don't know if it's completely set. I could rip it apart. I do see where it would delaminate, but it is certainly pretty solid. We'll let it sit a little longer. You should clamp it. In fact, let me get a clamp and do that. like these little clamps. There we go. Most kind of, particularly the adhesives that melt things, they generally do well when you clamp them together. Of course, if you clamp too hard, if there are things that are melted, you might squish a little bit. So that's one thing, PLA Gloop. Here's another. So this is a plasti weld. It's the same type of thing, but much thinner. It's very watery, where the PLA Gloop was, or Gloop was gloopy. It was really kind of thick. This one has kind of a, this one's more for very precise type things. So let's see if I can find some other thing. We got our temperature tower. Maybe we can glue it on there somehow. Now this one also is an older, didn't have a date that I see on here, but I know that this one's pretty old. But it works in a similar way, except that it's much thinner. So this one is not specific to PLA, where obviously this one is PLA Gloop, and it is more specific to PLA, but this is one that in general will do the same thing for melting plastic. Comes with a little applicator that you, basically this guy, let me show you. Now this one is pretty smelly. Not from where I'm at right now, but so you basically put this in here, squeeze some air out, and it will come up into the tube, and then you can use it. I'm squirting it back out now. And then you can use it as an applicator. I don't know if I want to try, and it's very finicky to get to flow out the way you want it, but it would glue similar to the way the Gloop does. And it's a little more generic, but it's a little more useful. I haven't tried anything like the PLA Gloop on anything other than PLA, but the Plasti Weld works on a lot of different types of plastics. Let me show you a different kind of glue that you might run across. So stuff like this, liquid cement, a lot of times this one will not work too well. In fact, let's give it a try. Let's try and glue this on, if it's not clogged up. But they a lot of times won't work very well on PLA because they're expecting the material to be styrene. A lot of these model glues, and obviously this isn't styrene. Let's see if I can find. We'll just try and bond it to this, it'll be fine. So you can kind of feel that it's adhering, but a lot of times it doesn't give a very good bond. We'll let that sit and see how well it does. There are other versions of this that don't work as well. That one actually seems like it might actually work. So there's all kinds of glue. You can use, I don't have a super glue here just because I don't have any super glue that's not dried up. That's the problem with super glue, is it dries up if you don't use it within a reasonable amount of time. The good thing about super glue is it does not go in and melt the parts together, so you at least have a chance of breaking them apart later on if you want to. Whereas this thing, by now, I mean, you can see it separating there, the corner. Remember, I didn't coat the whole surface here, so these corners are not actually bonded together, but that middle part, pretty sure I would have to rip one of the layers of material one way or the other for them to come apart now. Let's let that one sit a little longer. Same thing with this type of material. It bonds the material itself together versus gluing it together, so it's going to have a hard time of ever getting it apart if you wanted to. So these are probably permanently together, or we're going to have to break one of them to get them apart. Let's see what happens if we can. Actually, I don't even know if I can get it apart. There we go. All right, so we actually did get it apart, but you can see that we didn't coat the whole area here. We only had a little small area here. It's still a little bit tacky. So I think if we had coated the whole area and glued this thing together and clamped it together, we'd have probably had a pretty tight bond between these two. But, you know, it does look like it didn't completely finish. You can kind of see in this discolored area where there's a little bit of melting going on. Let's see what happened with this guy. Yeah, see this, it just doesn't do anything because it doesn't actually melt the PLA. That was the liquid cement. It gets you tacky and it will kind of hold things in place, but I don't think it's going to ever bond it together. So that's usually most of these type cements and model glues just aren't going to hold PLA together. This guy will. This is what's holding the mummy together. His leg, this one broke in two places and it broke over here at the ankle. I used that. This one is really nice for the small models because you have this tiny little applicator that you can, you know, get exactly where you want it. You don't want this stuff everywhere because it does melt the plastic, and so if you get it all over everything, that's just going to be a big melted glob of plastic. So you have these little tiny applicators to get it in there just where you need it. Super glue, like I said, is a good one for just holding things together, and it'll hold them together fine, but it will not like solidly attach them together. You can use some super glue and baking baking soda, not baking powder, and that will kind of fill in any gaps. It kind of makes like a paste that you can use to glue pieces together. I probably wouldn't use that on this little guy because he's so tiny. So you can do that. You can also do, maybe you do want something that you put it together and then you can take it back apart. So there's a couple of ways you can do that. I designed these little guys. Oh, I just realized that they are red and we're going to put them on a red mat here. We'll put them on the green part. And we'll just look down at them. There we go. So these are a couple of little springy pieces here. You know, they can open and close, and then here's just a part for them to fit in, and it's got a matching notch for the spring to fit in. So now I printed these a couple of different ways. I think actually these two are the same. This one's different, and obviously that one's different because it's got some longer arms on it that you can use to get the part out. So the main features here are you have one piece that has a kind of tapered. Now this one's a little bit stiff because it's kind of thick. In general, you want about 2 walls on this. Like, let's see if you can see them. We might have to go into the slicer to actually see the walls. But there are 2 perimeters here, and so you want to leave enough room for 2 perimeters here and 2 on that side. So if you're using a 0.4 millimeter nozzle, then that's 0.8 millimeters on one side and 0.8 millimeters on the other side. So you're at a minimum thickness of 1.6 millimeters across here, and that's getting close to what's going on here. This is a little bit wider, but that's getting close to setting this dimension more or less because of you want 2 walls on either side of it. You could probably get away with a single wall, but then your part's going to be relatively weak. These 3 I printed laying down like this. This one I printed standing up just to show you that orientation of the strands in your print do matter. Now this one, these I've actually used, they all work fine. This one I haven't even used because I'm afraid it's going to break the first time I try to pinch it together. Because in here, let's see if we can get close enough to focus on it. All right, you can kind of see how the light's reflecting. All the layers are going across here. And it needs to bend, like this hook needs to bend inward. Let's see. Okay, it can do it. Well, there it went. So that is more than likely what is going to happen. Now I have like a 20% infill, so it's pretty hollow in there. But you're not going to get many, if any, cycles out of something where you print it in this orientation and you want it to bend that way. These all printed flat, they have quite a bit of flexibility, and I don't feel any danger that they're about to break on me either. This one's actually pretty stiff because I don't have these long arms, but they work. Let's actually use this one first because it's easier to get out. So you can kind of see there's a little lead in here, so I just put a 45-degree angle and then a 90-degree overhang on the back to catch in the hole here, and you know, they will snap in there, and it is pretty solid, but you do have the ability to take it out if you want to. And so you can build snap fit type pieces. There's just a couple of design rules, I guess, that you want to follow. I think Cura finally opened. Let's see if we can look at a couple of these pieces. Let's see, they're in the same, I think here's the longer one. All right, so now in this orientation again, I don't know why you'd print it this particularly, what you'd want to gain by printing it on that end. You just don't want to print it this direction because all of your layers are going to be in the same direction as you're trying to move the part, and it's going to shear very easily, just like our piece did over here, where this would be called a shear failure, where it just sheared directly across the layers. The layers are generally weak, parallel to their grain, I guess you want to call it. So let's lay this thing down flat. All right, so let's see, we're set at, let's make sure we're on 2 walls. We should be. So here it's called shells in Cura, and there's wall line count of 2, wall thickness of 0.8. Those are directly related to one another. If you have a 0.4 millimeter nozzle, which is the default on most all printers you're going to get, then 2 of those walls would be 0.8 millimeters. So let's slice it, and let's go into preview and see if we can see our walls. Oh, we still have that raft turned on, but there you can see the walls. Let's get that gizmo off of there. Let's get all of the gizmos off of there. There we go. So you can see the walls. Actually, let's turn the brim off because it is, or the raft off. We'll do a skirt. It's getting too confusing. All right, they're much easier to see. Now, it might look like there are 3 walls, but there's actually only 2 walls. This innermost wall, if you want to call it that, is just the edge of the infill. Oh, actually, this is the top layer. Here's, maybe we can probably see it better on the infill. There we go. Now there you can see the 2 walls. This is a very low infill part, so there's almost nothing inside it. And all of your bending is happening in tension. You know, when you get this that way. When you push over here to close, or you know, to bring the hooks closer together, you're pushing. Let's get it in the same orientation, like that, pushing it in. Then these top layers over here are being stretched out. They're being in tension, whereas on the broken one, those layers were trying to do that, but it just broke across an individual layer. Here, it would have to break both of these strands by pulling them apart, which is much harder to do. The bottom ones are in compression. They are also helping, but as far as I know, there's not a way to only put certain number of walls on one side and not on the other side. There might be some tricks that you can make it do that, but there's not a thing that automatically does that. So you can see the 2 walls. Here's kind of that narrowest part. There's the 0.8 millimeter of wall on the top, 0.8 on the bottom, and then we could have probably made this a little bit thinner if we wanted to. I don't know why I made it the particular dimensions that I did. The important features are that you have this lead-in angle. It could probably be a little bit larger as far as you know, not encountering this step right away, but having a little more slope, but about a 45-degree lead-in so that your notch will not get caught on the edge of whatever it is you're trying to insert. And then you want a pretty much 90-degree feature on the back to catch inside the hole here, you know, inside the hole there. And then these radiuses, these curves here, those, in this case, I think they're 1 millimeter radiuses. You want those so that you don't end up with sharp corners. Anytime with any kind of mechanical part, whether it's printed or injection molded or whatever it is, if you have sharp corners, then you're going to create what's called a stress concentration at that point, and it's going to do exactly what its name says. It's going to concentrate the stress, and the stress is what makes the parts fracture and fail. And so if you have a very sharp corner there, then that's going to be a location for a likely failure. Here we've kind of radiused it, made it a fillet is what it's called, and that makes it less likely to have a stress concentration. It will still have some. Anytime you have a change in area from one size to another size, you'll have some amount of stress concentration. You're just trying to smooth it out as much as you can with these radiuses. And notice also that it's tapered. So it starts out wider and then it's tapered narrower. That also helps with, it doesn't have to bend as far to get as much clearance as you have here on your hook that's going to go in the recess on your part. So you can do these. You can build them into like little lids, snap fit lids, as long as you are careful about the way, the orientation you print the part that has to move. This part I actually did print standing up. It was printed just like this, and it should be fine this way. In fact, it would have been difficult to print any other way because it's hollow, right? So it would have had either a good amount of bridging to do. We probably could have printed it this way and only bridge across here, but this one doesn't have a whole lot of force that is trying to shear it, you know, make this part move this way like that. If anything, whatever it would be attached to would be trying to pull it apart, which there's still a lower amount of adhesion between the individual layers here, but they're really weak when it comes to shear, you know, going across the layer, making one layer slide past the other layer. The printed parts are really weak in that type of stress. So here you can kind of see, you can build these. Eventually they will wear out, although these are probably not having to do so much moving that they're ever going to be a problem until the material itself begins to degrade and your whole part has problems, but that could be years. PLA is biodegradable. It's a lot of these materials, including PLA, are a little bit susceptible to UV embrittlement, so they get brittle if they're exposed to UV light for hours and days and months or whatever. I haven't done any actual experiments to see just how long it takes for them to get brittle. ABS is particularly bad about that. PLA is probably somewhat bad, but it still should be years and years before you, under normal use, you have problems with this kind of thing. Let's see. Here are a couple of other things. Here's a common one. Let's get the cure out of the way. Here's a common thing. This is actually two things. This is the common one. So one thing, maybe you want some metal threads that you're going to screw some sort of fastener into. So here what I've done is, I'll actually show, yeah, it's over here. This is Simplified 3D. It's just a different slicer that I just show you a different slicer. So here's this part that we have right here. And you can kind of see on this one, I did 4 walls. You can see all 4 walls around here because these I want to be a mechanical, like, they're gonna hold a lot of stress. These circles, they're gonna have even more to deal with here in a second. But here's the slot that I have designed for this nut to slide down into, and then there's a, whoops, zoomed out way too fast. There's a hole over here. Now I did print this one. You can see this orientation. There's a hole here that the screw will encounter the nut and then, you know, bond whatever it's screwing together. I didn't build another piece for it. I guess it could have kind of created something for it to actually attach to. But how this works is you make, again, I have 4 holes. Now you can kind of see probably there's a little gap underneath there, so I have a little bit of problem on some of my top layer here. Kind of see one also on around the circle. It'll be fine for what we're going to do, but that's something you might want to work at, is getting that top layer to actually adhere to all these walls it printed. But I dropped it, I made it, measured the, across the flats of the little nut here, made this 0.4 millimeters wider, thinking that was kind of our tolerance. So it's, it's pretty tight. Remember, holes, features like this are going to end up 2 to 4% smaller than what you designed them, just because of the filament extruding into the hole, open area. But it's a nice fit there. Need to force it down. I think we did it. So it's down in there now. Now I have metal threads in a plastic part that I can screw this thing in with, and we should be able to get a decent amount of torque and clamping power if we were actually clamping anything together. I've just felt it engage the screw thread. So you want the 4 walls so that the edges of the nut here have something to hold on to, because it's wanting to turn, and so those walls are having to hold it in place while I tighten the screw that it's threaded into it. So this would provide plenty of torque and clamping strength for whatever you would want to attach there, and you can remove it, so you have permanent threads. Sometimes you can do this. I'll show this method on Wednesday, because it's related to Wednesday's topic, which is multicolor printing, which may not seem like it's related, but one of the ways we're going to do the multicolor printing is related to this. But you can also print these cavities, drop the nut in, and then finish printing over the top of them so that it's captured in there. Not that this one is going to fall out, but sometimes when you're got this thing oriented in all different directions, and the hole that you printed for the nut is a little bit larger than what I created here, then you turn it upside down and all those nuts fall out, and you've got a difficult time putting everything together. So there are ways to build the nut into the print. So print some, drop the nut in, print over the top of it, and it's there until it strips out somehow. This one, it's a little bit trickier, but where did they go? I gotta find them. Here they are. Actually, here's one. But these are brass inserts. Over here, they have threads built into them, which, let's see, I did have a screw that would screw into this one somewhere that I have lost. Let's see if this will fit in here. Yeah, this will fit in here. So they come in different lengths here, different diameters for different screw threads. A kit of these, let's see, I had some pulled up here in Amazon. Here's a kit that this is M2, 3, 4, 5. Those are all pretty common printer type threads. And you have different lengths here. This 460 pieces for $20. So they're not crazy. I don't know how often you would use these or not, but and you can get individual bags of just like one bag of the one we have here is somewhere in the range of $6 for 100 or something. All right, so but how they work. So you don't just force that. You might could. I don't know. I hadn't tried. But we have a hole. Again, it's got the 4 perimeters in it. And I made the hole. I may have made this one a little bit too small. Basically, I made it the size of this diameter here. So there's these ridges that stick out that are going to grab into the plastic. But I actually made the hole the size of this inner part right here. But then, like I said, the holes like this end up 2 to 4% smaller than what you are anticipating. And so it's actually a little bit smaller than probably needs to be. But it's got the 4 walls. I have this little tool. You don't necessarily need this tool. But it sits inside there. And then get all this stuff out of the way. You get something like a soldering iron, and you don't have to have this. You can go directly to here and heat set it in there. So it's a little bit tricky in getting it to not melt everything and getting it perfectly straight. So it does take some practice. This thing will help because it more evenly distributes the heat versus just kind of dumping it all at once in there. But we'll give it a shot and see if we can get this guy to set in here without too much trouble. I probably need some pliers though to kind of help orient it. And these pliers can act as a heat sink once it gets in here. The problem I usually have with these is that it stays hot for a while, and as you overheat it basically. So it doesn't start moving for a while, and so you keep adding more and more heat. Then once it starts, it's hard to get that heat back out and to cool it off. So I'm going to use these kind of as a heat sink also to hopefully not destroy ourselves. It won't destroy us, but we might destroy this plastic part. So I'm just letting it heat up. I've got it at 450 right now. That might be a little hot, but let's actually put it this way. So see, for a while, and you don't have a good way of knowing exactly when it's going to start, but you can see, all right, there it goes. And I did pick one of the largest ones that I have to try this with, so. All right, so let's. Well, all right. So you would keep adding heat, but see it's melting inside there. This one's a little bit large for this diameter hole, but the others I have are a little small for this diameter hole. And so you do have to, I would definitely, if you're going to use these, I would definitely, it's not too bad hot anymore. I would definitely do a couple of practice holes before you head off and just try it on your actual part you printed for a long time. Yeah, it's cooled down to the point now that I don't think I can force it in there anymore. Actually, I can. I might add a little more heat to it and try to get it to finish. But you can kind of see the problems are, like, it's deformed this entire area around here, getting it hot enough for the plastic. Even with 4 walls, they're a little bit tough to use, but they are an option. So let's get a little more heat in there and see if we can get it to set the rest of the way. We'll do it this way. Close. Just having to push all this plastic out the back too. And if you do too much, like wobbling around, then there's no material left to actually hold your piece that you're trying to insert here. So you take some practice. I don't practice enough with these things, but we did get it in there. I don't know how exactly straight it is. It probably could go a little deeper, but got a good bit of deformation across the top, so we probably weren't quite hot enough. And we've got a bunch of plastic inside there that it's going to be in the way when we go to try to put our screw through there. Get that out. All right, let's see if we can grab it out of there. All right, now from this side, we've got some nice threads. The other side, yeah, it's a little bit deformed around there, but now you do have metal threads that you should be able to screw into. I've got some plastic still in the threads. There they go. And so this is another way. I actually think if you can, the captured nuts over here are probably a little bit better, but this is another option. Maybe one thing that these can be used for is places where you can't fit a captured nut. So maybe it's a boss, basically a cylinder that's inside of an object, and you don't want to have this big block of material around it to hold one of these, or to hold a nut. You can build a cylinder up and put one of these in there. They are a little bit difficult. You can kind of see it's a little crooked. You can kind of see that that bolt is not perfectly perpendicular across this plane. So once you kind of get them in, it's kind of hard to go back and adjust them, though. If you add more heat, yes, you can, you know, kind of twist things around and straighten them up. But it's eventually going to get to where you've just melted the whole plastic all around the hole here, and there's no holding power left. So they're another option. I actually like these a little more, but they do have some options for the smaller ones in particular are kind of handy, because once you get to a nut that's smaller than this one, it's tough to make a hole that's just the right size for it to hold in. Those smaller nuts are, and now this is pretty small, but if you needed something that's even smaller than that, you might have to go to one of these type of inserts, or just make the hole itself and try to directly screw into it. So let's see if I can find a good sample real quick. They do make plastic thread screws, so screws with threads that are specific for plastic. I don't see any right here with me. I should have thought about that. But let's see if I can find, here's at least a coarse threaded screw. So a screw like this one, let's see if we can get closer to that guy. So screw like this one has much coarser threads on it than one like this. These coarser well, we're still off the screen. There we go. These coarser threads are good for, don't use any kind of nut or these threaded inserts or anything. Just screw them directly into the plastic. In general, with these type, what you do is you measure, oops, don't drop that. You measure the root diameter, so kind of but in between the threads, and make the hole that size in the CAD program, and then once you print it, it'll be again a little bit smaller, and that should be about the right size hole for one of these screws to thread itself into. You may not get as many cycles, so you might not can thread it, unthread it, you know, tighten it, untighten it over and over again. But you'll get a couple of cycles out before the threads in the plastic just kind of degrade. And you can't put as much clamping torque. So if it's something you really want to clamp down on, then these are very likely to do that up to a point and then just rip all the threads out, and you won't have anything in there. You'll have to go back and put one of those threaded inserts into the hole that it left. But there are some plastic screws. Let's see if I can find an example. Here's one. Let's see how this one has this big spiral and these relatively deep threads on it. You can find some that are specific, some screws like this that are specific for screwing into plastic. A lot of times they'll have two threads, a really deep one and a shorter one. I don't see any of those here, but you can see how deep the threads are on these plastic screws. Yeah, I don't see the other kind that I'm thinking of, but these can be very handy to have if you're trying to screw plastic stuff together and you don't want to deal with the nuts that you insert or the threaded inserts that are the heat sink ones. Looks like you can get 100 of them for in the $10 range, so 9 or 10 cents a screw. So they do have those type of things also for attaching things. One other thing that I don't really have a way because it's so noisy to show you how to do. But you can take, and there's actually a toy when I was little that did this. I don't think they make these kind of things anymore, but you can take a piece of filament, put it in a Dremel, something like a Dremel. You could use a drill, but they're kind of hard to hold. And you can go in and basically friction stir weld two pieces of plastic together. I'll probably have to like demo that somewhere else so I can turn the volume down, because the Dremel is just going to be too loud on the camera the way it's set up right now. But it's an interesting thing. It's very imprecise. Let's see if I can find something on FrictionStir Welding for plastic. Normally this is FrictionStir Welding's for metal, but let's see if we can find a picture of one. There's kind of one, but I wanted to see. Well, here's a metal one right here where they are literally turning this piece and welding two pieces together. That's not a great one. Normally, I don't know that this gets used for plastic very often, but friction stir welding is a way to, you don't put like electricity into it, like an arc. It's not heat like a flame. It does create a lot of heat because the heat is created from the friction, but you can do that with a Dremel and a piece of filament, and basically run the filament as the Dremel's turning, run the filament across the gap or the join that you're trying to connect together. I'll try to demonstrate that. It's kind of finicky and not really that great of a process, but you can do it. You can also just melt pieces together. That gets kind of fumy and not toxic necessarily. It could depend on what you're melting, I guess, but there are difficulties in controlling it. We had enough trouble trying to control this little guy over here. You know, keeping the heat controlled on that one. If you're interested in the snap, you know, the hinges, things like that, I would encourage you. There are several print-in-place models that are you fold them. So sometimes it's called 4D printing. There's a really good set of them at this site over here, fab365.net. And these are, I wonder if he has a picture of one printed out flat. There it is. Well, here's the Dragon module, but they print no supports. At least I think all of them, this particular brand has no supports. And you can see here's some of the clips that he uses, prints it all flat, and it's all hinged together. You fold it up into a three-dimensional object. So why I would tell you to look at these if you're interested in hinges and snap fits and all that is that there are good examples of 3D printed, designed specifically for 3D printing on FDM printers, so not on resin printers or anything like that, but something that like your Ender 3, and you can get a good idea of how to actually go in and see some of these hinges, some of the snap fits, and these are, you know, they're $5 each or whatever, but you can kind of see the approach that he takes, and you can see similar things to what we talked about with the he's printing these little notches. He's printing them in the same direction so that the strands of them are in tension, not in shear, and then they're going to seep down into these cavities over here. Now in this case, these don't come back apart a lot of times, but that's still okay. You can get the idea of how they fit together in the first place. I think we've got a decent amount of different ways to adhere things. Let's go back. I should have left our get all these pictures off of here. There we go. I should have left these together to see how well they do. I did leave these together. See, there's nothing there with the with the model glue. So you really have to use something like super glue or the PLA Gloop or the Plasti Weld, something like that, to be able to hold these pieces together. The type of glue that you might have for building a model or something like just isn't going to hold PLA. Now I don't know if it holds ABS. I don't know if that's close enough to the same composition of styrene that it would melt, but the PLA certainly does not with regular model glue. So get you some, even if it takes, you know, $10 or whatever for a bottle of the stuff. If you plan on gluing PLA together, you're going to have to use something that is either specifically formulated for PLA, like PLA Gloop, or something that is for plastic in general, and melt those layers together, clamp them together so that it holds in place until it's finished curing or unmelting, I guess in this case. And you should be okay. Don't forget that you can actually use mechanical fasteners. You can screw directly into plastic with the right type of screws. You would have a hard time with these screws that you get with your kit. Your printer kit are probably not going to do very well for screwing directly into plastic. You need the coarser threads of something like this, or get some of the plastic specific screw threads. In fact, I might order some so we can see just how strong they might be. I think we're good for today. On Wednesday, we will do some multicolor printing. And I'm going to do some multicolor printing that does not require any special hardware. We're going to do it through software, through slicing certain ways, maybe interjecting some G codes so that we can change out our filament. And we'll do some of that. And I will show you some ways that require some hardware, just so you know what they look like. And if you're interested in some of those methods, then you do have to make an investment to get to the other type of multicolor printing. But don't think you can't do multicolor printing because you just have an Ender 3 with one nozzle. You can still do it. It just takes a little bit more thinking on the front end of how you're going to do it. All right, that's what we'll do on Wednesday. I'll see y'all then.